one of the important things was the CIP priority rules for assigning priorities to functional groups, because we need this in for two different things. One is to name a double bond, either E or Z, and you're going to have to be able to draw these out as well. So you've got to know these rules. And the other thing is for naming chiral centers, either R or S, and for that you've got to know this. I have an example here with just a double bond to start with, just to remind us about what we've done. So this is the double bond that we're assigning E and Z priority to. I hope that you can see that this one does not have an E or a Z isomer to it. If you don't see that, please come and speak to me about that, because it's important. All right, so if we're assigning E and Z priority, we want to see, do we have the highest priority groups on the same side or on opposite sides? So let's start with the right-hand side of the molecule. We'll look at this, and remember, CIP rules, we work one atom at a time. All right, it's almost like sort of like levels. So we're not looking at the whole group. We go, what's bonded to this carbon is a carbon. What's bonded to this carbon on this side is a carbon. And carbon are the same, so there's no difference there. Then this carbon is singly bonded to another carbon, whereas this carbon is doubly bonded to a carbon. That double bond takes priority. So even though this carbon is bonded to two carbons, we're just moving down one path, and when we move down that one path, this one wins out. So the highest priority is there. All right, on the other side of the molecule over here, we do exactly the same thing. We start off with our carbon that we're looking at, and here, this goes to a carbon, this goes to a carbon, there's no difference. This carbon goes to an oxygen, all right, it is doubly bonded to it, but it goes to an oxygen. This carbon goes to chlorine. The chlorine wins, all right, the chlorine wins out because it is a much higher molar mass, and so this side must also be the highest priority. And because the two highest priorities are on the same side, this becomes a Z double bond. All right, you need to make sure that you're able to do this. Your tutorial and tutorials from now on, tests and exams will have something like this in it. So you must know how to do this. It's guaranteed. Now the hard part for you as a class is starting to appreciate chiral centers. I'm going to draw up the most simple or a simple example, which I use a lot in class, and that's just butanol or 2-butanol. All right, very simple. It has one chiral center there, and let's just remind ourselves about what a chiral center looks like. I don't have the full model here, but I've got a tetrahedral little model here, and if we imagine this carbon here to be our tetrahedral carbon on the molecule there, and maybe we'll have the red as the oxygen, the white as the hydrogen, which is going towards the back. We don't see it, but it is there. We don't have to draw it in. If you want to draw it in, it's fine. We can redraw the molecule, something that looks a little bit like this then, if we want to make it neat. All right, and there we see the hydrogen going towards the back. All right, but we don't have, so long as we can see it in our minds, it's fine that it's there. And so if the methyl group is this blue plastic bitty, and the ethyl group is the green one, so the molecule, as we've drawn it, would look a little bit something like that. Now, you see, this is flat, and this is not. And so it's really difficult to draw out something that's flat but represents something that's not. And so that's why we use these wedges and dashes. But just to get some sort of appreciation, you can see, if I try and swing it a little bit this way, how this one over here is trying to represent this. Okay, so it's not easy to try and do it, but that's the best that we can do. Now, the Cahn-Ingold-Prelog rules for assigning stereochemistry to a carbon say that we need to assign priorities, all right, just like we did before on the double bonds. We need to assign the priorities, and then we have to put the lowest priority towards the back. So in this little model here, The lowest priority is going to be our hydrogen, all right, always going to be hydrogen if there is a hydrogen because it's the smallest group. And so if we stick it to the back, we now have to look at it like this. And if we look at it like this, the highest priority is going to be the OH, because oxygen is higher than the carbon-carbon, all right, or the carbon and the carbon there. And then the next highest priority will be the green one, which is the ethyl, because carbon going to carbon will have a higher priority than carbon going to just a hydrogen. All right, so hopefully you can see that from the CIP rules. And so as we look at this, we're going from this to this to this. We're going round, all right, in a kind of a clockwise direction, all right. You turn your wheel of your car in this direction, you go towards the right. And when that happens, the answer is it's R. If I draw this out differently, I now put the biggest group going towards the back, all right? So that means actually the smallest group is coming towards us. Then what we're looking at is we're looking at it this way round. Actually, no, it's all wrong now because the green was the ethyl. So we actually have to swap them around, the green and the blue. So we do that. And that makes sense because we've just taken the mirror image of this. And when we do that, we're actually switching around groups. So now you can see the hydrogen is coming up towards us. We've got the blue methyl and we've got the green ethyl over there. And now we want to assign the CIP rules. It's still going to be 1, 2, 3. But the problem is we're looking at the hydrogen. It's coming up towards us. And so the problem is what we need to do is we need to flip the whole thing around in order to assign it. Now, not many of us can do that, all right? When we're looking at something flat on the page, it's fine if we've got a model, but if we're looking at something flat on the page, it's difficult to do that. So because we can't really do that, what we do is we leave it looking up towards us, and then we work it out as we would have normally, 1, 2, 3. So in other words, we're going round and round to the right again, 1, 2, 3, but we're looking at it back to front. In fact, what we should be doing is looking at it this way, and now we go 1, 2, 3, all right? And so now we're actually going in an anti-clockwise direction, all right? So anti-clockwise is S. Just remind you again, when we looked at it this way, all right, when we looked at it this way, it looks like it's going round towards the right because we're going 1, 2, 3, but we're looking at it back to front, and therefore we are actually, this is the incorrect way, and it must be the opposite of what we're looking at. And that's the most critical thing that we need to get to. I noticed in class that some people had some problems with the fact that I seem to be putting the largest group either pointing up or down. Remember, we could redraw this molecule like this. I could put the OH there, and I could put, say, the methyl group coming forward. All right, that's exactly the same molecule. All right, the hydrogen's still going towards the back, and our assignments are still the same. 1, 2 for the ethyl, 3 for the methyl. We're going 1 to 2, 2 to 3, 3 back to 1. We're going round towards the left, all right? If we turned our steering wheel of our cars, we go round towards the left. And because the hydrogen is going towards the back, we're looking at it correctly. So going around to the left, this is S. So in other words, this molecule here and this one over here are exactly the same molecule. All right, they've just been drawn out in a different way. They're exactly the same molecule. And it's very difficult to see that this and this are the same. But if we assign their chiral centers and we see they are the same, we can recognize that.